There is a common type of factorization. It is a binomial, and it is called the difference of two squares. We call that a dots. As you can see, it is a difference. We have subtraction. There are two of them, so there always will be a binomial. And both terms are perfect squares. Perfect square, perfect square, perfect square. And so, we notice that there seems to be a trick whenever we get a binomial. When you think about our foiling, the middle terms cancel out, which means one has to be positive and one has to be negative. The fact that these are squares, both perfect squares, mean it's going to be the same thing. So that means that when I FOIL, my outer term and my inner term cancel one another out, and I'm left with only a binomial of perfect squares coming from the first and the last. So as you learn to recognize that it's subtraction, it's a binomial, and they're perfect squares, you'll start getting very good at just taking the square root of both terms, making one positive and one negative. Take the square root of both terms, make one positive and one negative. So x squared minus 100, you're going to have x minus 10 and x plus 10. X to the 6 minus 4, you might be thinking, that's not a perfect square. Okay, 6 is not a perfect square. X to the 6th, however, is an even exponent, and yes, it is a perfect square. If you're not sure, FOIL it. F, O, I, L. Great. X to the 6 minus 4. In the same way that you just thought x to the 6th wasn't a perfect square because it's 6 is not a perfect square, I want you to realize that x to the 25th, even though, yes, 25 is a perfect square, x to the 25th is not a perfect square. Perfect squares always have what kind of exponent? An even exponent. So this is considered prime. You cannot factor that. Let's look at x squared plus 49. Cool, 2 squares. Love it. This is prime. Why? Because it's addition. It's not a difference of 2 squares. You will come across having to combine, taking out the greatest common factor and then using the dots technique. So we'll remove a 5 from both terms. You might think you're done factoring, but you're not. We'll keep our 5, but now let me try to break this binomial into 2 more binomials. Let's see. Is this a GCF? I might be tempted to pull something away and out of both of them, but I don't see any common factors. Oh wait, both of these are perfect squares. We have 6k and 11y. So I could just write 6k minus 11y and 6k plus 11y. And then it's factored. Notice whenever you factor a dots, one's minus, one's positive, and they're exactly the same otherwise. Well, those don't look like perfect squares. This can't be a dots. It needs to be the difference. Okay, I got that, but it needs to be the difference of 2 perfect squares. Oh, okay, wait, let me see. I can't factor out a 4. What if I factor out a 2? 16 minus 9q squared. Oh, it is a dot, so now I need to factor this. So 2 times 4 minus 3q and 4 plus 3q. Here's the most dangerous part of dots, is when you can keep going, keep factoring. So I have 2 perfect squares here, x to the 4th minus 4, x to the 4th plus 4. Sweet, I'm done. Let's move on. No. Ask yourself, can you keep factoring? This is not a difference of 2 squares. It's a sum. You can't do anything with that. That's done. That's factored. That's prime. But we can still factor this difference of 2 squares. And don't forget, we need to bring this down, because only once I multiply all of these together will that produce this binomial. I need to ask myself, can any of these be factored? Well, we already decided this is a sum, it cannot be factored. This is a sum, it cannot be factored. This is a difference. It's a difference, but oh wait, this is not a perfect square, so it's not going to be a dots. So we're going to consider this factored. The end. The tricky part